I'm Evan Piermont, and I'm going to be talking to you about my paper, Hypothetical Expected Utility. In order to assess the optimal action in an uncertain environment, the decision maker must contemplate the effect of each action in different resolutions of uncertainty or different hypothetical contingencies. And there's a host of evidence that real-life decision makers do not do this perfectly, and in fact, a growing consensus that many economic anomalies can be traced back to this failure to think hypothetically. For example, in voting models, in experiments of voting models, it seems that agents do not correctly condition on being decisive in the election, on being the pivotal voter. Likewise, the winner's curse is in effect not conditioning on the hypothetical implication that if I win the auction, I have the highest and therefore likely over-optimistic valuation of the good in question. And in disclosure models where types reveal themselves voluntarily, a rational agent should understand that no news is equivalent to bad news, and that's not always the case in experimental or empirical findings. So this paper proposes a model of flawed hypothetical thinking that allows a decision maker to have a subjective and potentially incorrect assessment of hypothetical events that is simple, general, and identifiable. And what I really care about here is that it can do two things simultaneously. It can represent the objective, say, mechanical version of the uncertainty, right? The modeler's view of the uncertainty, and also a subjective interpretation of that mechanical uncertainty. Because to represent, in an applied sense, the real true strategic considerations of an agent, we must know both what is actually going on in the world, the objective world, and also the interpretation or the incentives that are apparent to the decision makers themselves. And of course, we want this model to be have this desiderata, in particular to be identifiable from decision theoretic and really simple decision theoretic objects. One of the merits of this paper is that it provides a new perspective as to what we mean when we say hypothetical thinking. And the answer to this question, what is hypothetical thinking, that I'm going to show you in the next, in the rest of this video, is that it's a notion of understanding implication. That we could just look at what the decision maker understands about how one hypothesis implies another. Does H imply G? Does G imply F? Etc. And from this, build a global notion of an interpretation of each hypothesis. So we can take a relative notion, which is local and is determined by just the relationship between individual pairs of hypotheses, and from that build a global interpretation or an absolute notion of how these hypotheses are interpreted. And this is not unlike the relative absolute notion between preference and utility, a local comparison being built into some global value. So a standard model of uncertainty consists of two things: a state space, which is capital omega, and a measure over that state space, which I'm going to call mu. And then a hypothesis, so some hypothetical event, is just a collection of states, right? So the hypothesis that it's raining outside is the collection of all events where it's raining outside. And that is a subset of the state space. So mu is a measure over the state space, and it captures the decision maker's uncertainty about the particular hypotheses in the obvious way. The probability that H is true is the probability of the state, the event H. This is really the way that uncertainty is modeled in pretty much all of economics. I'm drawing a picture for no reason. We have a state space, we have a probability that assigns values to each state, and then we think about some hypothetical event H. Maybe my payoff depends explicitly on H, and the probability of H is given by the mu probability of the states aggregated over the event. So what I'm going to do here is just the smallest little twist, and I'm adding one object to the model, and that is that the decision maker does not properly interpret the hypothesis H, and so she interprets it as some other event, right? So we just have to say, well, I'm not interpreting it as H, what am I interpreting it as? And that's given by this mapping pi. So I'm going to call pi an interpretation map, and it just takes each subset of the state space to a new subset of the state space. potentially the same one, I mean new in the weak sense. And, and I'll call pi of h the interpretation, or the decision maker's interpretation of h. This is the only addition to the model, is that each event is interpreted as a possibly different event. So an interpretational model of uncertainty, what I'm going to consider myself with in this paper, is now the same two initial objects, a state space and a measure over it, and what I'm adding is this interpretation map. Now the decision maker's uncertainty is no longer captured by the probability of h, but rather the probability of the interpretation of h. So going back to our picture, we have the same hypothetical event, but it's no longer interpreted correctly. The decision maker accidentally includes omega 1 in the event h. And so this interpretation is different, and the probability of the interpretation, the probability of the event from the perspective of the decision maker will also be different as it's filtered through this interpretation. And so we see that mu h, the probability is not mu of h, but mu of pi of h. Of course, at this level of generality, anything goes. It's very hard to describe behavior or really even interpret the model. And so we're going to instead consider a decision maker who is almost rational. Of course, the rational decision maker has an interpretation map that's the identity. The interpretation of each event is the event itself. And we're going to consider a decision maker who's almost rational, with just enough flexibility to capture all of the empirical failures to hypothetical reasoning without letting it get too wacky. So there's three conditions, the first of which is truth. And truth says that the decision maker never rules out the true state of affairs. So for any contingency, any state in the state space, if it's in H, it's also in the interpretation of H. The second is introspection. If the decision maker cannot distinguish between her interpretation of an event and the event itself, right? So her interpretation, if she looks at H, she interprets it as the right-hand side of this pi of H, and if she then further interprets that event, it has to stay the same. Because if these were different events, then the decision maker in her mind could understand introspectively that she has a flawed view of the world, right? Because when she keeps interpreting the same thing over and over again, it keeps moving. And finally, consistency. So consistency says that if some event, if some contingency, state in the state space, can be ruled out both by H and by G, then it can be ruled out without knowing whether or not H or G holds. Right, so, and likewise, if something is in both H, in either H or in G, then it's in the union H or G. So it says that this interpretation map distributes over unions. We're going to call a interpretation map coherent when it satisfies these three restrictions, T, I, and C. So before diving into how implication can identify this interpretation mapping and the connection between the two, I just want to show that the model with this interpretation map can explain empirically relevant phenomena, can explain well-known deviations from optimal behavior. And in particular, the Monty Hall problem or Monty Hall paradox, it's a paradox because people come to the wrong conclusion, not because there's any fundamental tension in statistics. So it comes from a 1963 game show called Let's Make a Deal, the winner of which at the end of the show was presented with 3 doors. And behind 2 of the doors was a goat, and behind the third door was a prize, a desirable prize. And the decision problem works as follows. So the host, Monty Hall, the namesake of the problem, knows the contents of the doors, and of course the contestants do not. Right? So the decision problem works as follows. First, a contestant chooses a door. Then, Monty Hall opens one of the 2 unchosen doors. And critically, he always reveals a goat. So he never opens the door with the prize. And because he knows the contents, he can do this 100% of the time. And then finally, the contestant is afforded one more choice. and that's to keep the door initially chosen or to switch to the other unopened door. And assuming that the contestant wants the prize and not a goat, what should he do? Right, that's the Monty Hall problem. And we're going to analyze it with a very simple four-state model, and we reduce the complexity by assuming that the contestant always chooses door 1, and that's without loss of generality by relabeling the doors after that initial selection. So there's 4 states. Omega ij is that the prize is behind door I, and Monty opens door j, and they're labeled pictorially here. And given that everyone is randomizing uniformly, the probabilities over the states are given by mu above. So the event in question, say, is that Monty Hall opens door 3. And we ask, what should the decision maker do? Should he switch to the other door, which is door 2, or should he stick with door 1? And we can analyze this using simple conditional probabilities, and you see that the probability if you stick is 1/3, and if you switch is 2/3, the conditional probability. And this is symmetric in door 2, so if Monty Hall instead had opened door 2, then the same would apply. Switching doubles the chance of winning relative to sticking. Now, the reason this is called a paradox is because countless intelligent people vehemently reject this conclusion, and they feel very strongly that there should be no benefit to switching doors. And their specious reasoning is built out of the following observations: that 1, the initial bias, there's no initial bias between doors 1 and door 2. Everything is symmetric. And when Monty Hall opens door 3, this is unrelated to the contents of door 1 and door 2. It doesn't change what's behind them. And so this symmetry between door 1 and door 2 should remain unbroken. And therefore, there should be no benefit to switching doors. But such a contestant fails to reason hypothetically. And they fail to understand what the world must be like in order to get that information, that Monty Hall opens door 3. And looking at the bottom bullet point, what we see is that the contestant ignores a specific piece of information, which is that Monty Hall could have opened door 2 only when the prize is behind door 1. And so the fact that door 2 was not opened reduces the probability that the prize is behind door 1. And this event didn't happen, right? So it reduces the probability that the prize is behind door 1. So because they're ignoring this piece of information, the contestant conflates 2 distinct events: that Monty Hall opens door 3 and that the prize is not behind door 3. Now, of course, if Monty Hall opens door 3, it implies that the prize is not behind door 3. So there's an implication between the first and the second statements in the first bullet point. But by conflating them, they're adding an implication in the other direction, right? That these are, in fact, the same event when they're, in reality, distinct. So we can create an interpretation map that reflects this conflation of events. So Monty opens door blank will be identified with the prize is not behind door blank. And so the interpretation of O2 and O3, opening door 2 and opening door 3, are given by these 3 states on the right-hand column. All other events are remained unchanged, and it's easy to verify that this is a coherent interpretation map, so it satisfies truth, introspection, and consistency. Now, redoing our conditional probability assessment, but using not the true probabilities of hypotheses, but the interpretation, the probability of the interpretation, we see that the event in question is O3, and it's interpreted as these 3 states: omega 1, 2, omega 1, 3, and omega 2, 3. And here, the conditional probability from winning is 1/2. It's the first 2 states, and the conditional probability from switching is 1/2. It's the final state. And so we can see that there is indeed a symmetry here, that a contestant with this interpretation of hypotheses, who ignores this additional piece of information because Monty opened door 3, would indeed be indifferent between switching and sticking. So all of this is to say that this relatively simple addition to the standard model of a pretty close to rational, but not quite rational, interpretation of hypotheses can explain empirically relevant phenomena, right? So actual behavior in the laboratory or in game shows. Now we come to the meat of the paper, which is the relationship between implication as perceived by the decision maker and his flawed interpretation of these hypothetical events. Now, in reality, in the physical universe, it's snowing implies it's cold. So the hypothesis HS implies the hypothesis HC, and that's because whenever the first one is true, the second one is also true. And another way of saying that is any contingency or any state of the world contained in HS is also contained in HC, which can be written very succinctly: HS is a subset of HC when viewed as events in a state space. Now, a decision maker with flawed hypothetical reasoning will not perceive the true implication relation, but rather the subjective implication relation given by her interpretation. So a decision maker perceives that H implies G, which we write using this implication arrow, just the arrow, is true when pi of H is a subset of pi of G. So not when H really implies G, but rather when the interpretation of H lies inside the interpretation of G. Now, if we work our way back to the example, we can see that the two events in question were Monty Hall opens door 2 and the prize is not behind door 2. And the contestant mistakenly identifies these two events, treats them as though they're the same. In other words, treats them as though there's a bidirectional implication between them. So he correctly perceives that O2 implies not P2, since whenever Monty Hall opens door 2, the prize is not there. However, by identifying two distinct events, he incorrectly perceives the other direction of implication, that not P2 implies O2. And this is not true because not P2 could be true, the prize could be behind door 1, and yet O2 is not true, door 3 could be opened. So a decision maker who fails to extract all the information from the hypothesis at hand will in general perceive too many implications. And the reason that they perceive too many is exactly like in the example, they are conflating distinct events. So you're taking two events which are actually in reality different, and you're treating them as though they're the same because you're not extracting the information to be able to distinguish between them. And by treating two events the same, you're creating an implication where there isn't one, right? Because one is not a subset of the other, and yet you're acting as if they're the same set. So the axiomatic character of this paper is, what if we start with this implication relation, which remember is a subjectively derived thing from this decision maker rather than the interpretation map. And of course, one might still ask, well, where do you get this implication relation from? That's not observable. And I will cover that at the end of the talk and really in detail in the paper that is itself derivable from preference, from choices over Ansgar-Almanac. So if we just observe this implication relation, it falls from the sky, what might we ask of it? Well, we would want it to be transitive, right? I mean, these are rationality axioms, which are not the full rationality axioms, but are pretty close. So we want it to be transitive. If H implies G and G implies F, then H implies F. So this is that the decision maker perceives the true transitive nature of cause and effect that pervades our actual universe. The second is monotonicity. So if H is a subset of G, in other words, if H in reality implies G, then he perceives that H implies G. So the decision maker never inverts the order of objective implication. So when, it never goes the opposite way, right? You perceive the ones that are there. You might perceive extra, and that's as described before. Deduction says that if H implies G and H prime also implies G, then I don't need to know which H or H prime is true. I can deduce G. So from the fact that H implies G and H prime implies G, now remember that these implications are subjective implications. So from the perception that H implies G and the perception that H prime implies G, the decision maker does not need to know whether H or H prime is true, just that one of the two of them is true. So deduction is a closer to a introspective axiom that if I perceive certain kinds of implications, I can from that deduce other further implications. And finally, decomposition. And this is the only axiom that's sort of complicated enough to warrant an example. And that's that if F implies some joint hypothesis, so F implies H or H prime, then there exists, then I'm positing that there exists a decomposition of F into a G and a G prime, such that G implies H and G prime implies H prime. So complicated implications, F implying something, a joint event, a union of events, can then be broken down into two distinct, not necessarily distinct, they could be the same, two separate implications, G and G prime, and G and G prime aggregate back up to F. So an example would be, say F is some statement and implies H, the student in my class did very well on the exam, or H prime, that the student did very badly on the exam, but doesn't determine which of them is true, just determines that it's jointly true, and one of the two of these is true. Now, what I'm asking is that F can be decomposed into two separate things, one which implies H and one which implies H prime. So maybe F, something that could imply these two things but doesn't tell you which one is true, is maybe the student left this 2-hour final exam within 20 minutes. And then we can decompose this into two reasons or two kinds of events which cause F to happen. And that's the student's really smart, understands the material really, really well, and leaves in 20 minutes, does really well. This implies H, or doesn't have any idea what's going on and realizes that they're not going to do well and leaves very quickly because they're a terrible student, and that implies H prime. So the axiom says that such a decomposition always exists. Now from this, we can create a coherent interpretation mapping. So this is like a representation theorem, but instead of representing utilities, we're representing implication. We're representing the logical relationship between hypotheses. So if Clunk satisfies, if the implication map satisfies these four properties, then there exists a coherent pi such that H implies G exactly when the interpretation of H is a subset of the interpretation of G. And this is identified in the sense that mu is unique. This is the only mu that does this, the only coherent mu that does this. There might be other non-coherent ones. And the proof is very simple. I'll give it to you in one line. You take H and you map it to the union of all things that imply H, subjectively imply H. Now this is very canonical in the sense that because pi is unique, this is the only map that works. So the proof is just showing that this satisfies the coherency axioms, the coherency restrictions. But I mean, this is it. This has to be it. Right? In the paper, I consider other weaker characterizations, all which use this same structural mapping from an event to everything that implies that event. And you can show that there's certain things that are inherited by that mapping. So you weaken conditions on the implication, the subjective implication, and you weaken conditions on the interpretation map. It's worth pointing out that uniqueness relies on the properties of pi, so there may be other non-coherent interpretations that rationalize the same behavior or rationalize the same implication beliefs. And just a curious aside, if pi also preserves the empty set, then the image of pi is a topology on the state space. So this is as far as I know, novel axiomatization of the topological axioms. There's a lingering concern, alluded to earlier, that this implication relation is not potentially observable, right? We have this result that says if you start with this relation, you can move from that relative comparison between hypotheses to an absolute notion of interpretation that embodies this decision maker's hypothetical view of the world. But that's only so good if we have the ability to identify this thing that we're taking as primitive. So we need to start with something even more primitive and build it from that observable object, which of course will be betting behavior or preferences over acts. So in the paper, I deal with general Anscombe acts, but in that case, you have to deal with how you aggregate across different events, and I'm going to ignore that for this talk, but it is there if you're interested. For now, I'm just going to concern myself with bets on hypothesis. So a bet is an indicator function on the hypothesis. It pays 1 utile when H is true and 0 if H is false, right? A bet on H. And it's denoted by BH. Then a triple, the state space, the interpretation map, and the measure over the state space, is an hypothetical expected utility representation of our preference over betting behavior. If whenever a bet on H is preferred to a bet on G, then that's exactly when the probability of the interpretation of H is bigger than the probability of the interpretation of G. So the subjective assessment of the likelihood of H is bigger than the subjective likelihood of the assessment of G. So how can we build this representation, and in particular, how does it distill or identify, reveal the decision maker's perception of implication? And to do that, I think we start with the idea that, all right, the decision maker interprets, it perceives that H implies G. This is subjective. How does she value a bet on G versus a bet on G or H? Well, by assumption, she assumes that whenever H is true, G is also true. I mean, we assume that she perceives that whenever H is true, G is true as well. That's the definition of this perception of implication. A bet B G union H is a bet that either H is true or G is true. And so when does this pay off? Well, if G is true, then it pays, right? Because that's a sufficient condition for it to pay. And also a bet on G pays, of course. Now, if G is false, the decision maker, through this implication, must also perceive that H is false, right? That's the contrapositive of this implication. And so that means that neither G union H nor G is true, right? And so neither bet pays off. So in other words, she's indifferent between a bet on G and a bet on G union H. And we take this particular indifference to be the indicator that the decision maker with such a preference perceives H implies G. And we're going to write this H squiggly implies G. And if you get nothing else from the paper, take away this notation. It's, if I might toot my own horn, brilliant. It's an equal sign with the little clunk arrow, and it looks like the implication arrow. So we're going to say that H is revealed to be implying G if, when you have a bet on G, the additional value of also winning if H is true is 0. There's no additional value in having G and H be true. Now, why is this? Well, it's intuitively because if H implies G, then whenever H is true, G is true too. So if I already win when G is true, and you tell me that you can also win when H is true, well, every time that additional flexibility comes into play, G was already a winner. So to connect these things, if we have an HEU representation, then if H is perceived to be implying G, we have that in the representation, pi of H is a subset of pi of G. In other words, we can, from this preferential thing, go through the result from before, right to the interpretation mapping. So we can from preferences distill the interpretation mapping, right? Another way of saying this is that the perception of the revelation of perceived implication, this squiggly implies, has to be matching up to the actual implies, right, through the chain of if and only ifs. Of course, there's some technical regularities here to make sure that we're dealing with zero probability events, but other than that, we're fine, and you can look at those in the paper if you're really a stickler for zero probability events. Finally, and I'm running out of time, so I'm going to write it in the best possible way, is Clunk satisfies some reasonable axioms if there exists a unique HE representation. And really the point is that from restrictions on preference, we can get back the restrictions on this derived implication relation. And it's not worth really going over what those axioms look like. They're in the paper. They mirror, in some sense, the axioms for the implication itself, but they do have their own behavioral characterization and interpretation. But the point is that we can start, the takeaway from this slide is that we can start with a preference over bets, and from that identify and construct a unique hypothetical expected utility representation. That's pretty much all I'm going to talk about. I do want to highlight a few other things that come up in the paper. Of course, as alluded to, I deal with general acts rather than just bets. There's also a relationship between the interpretation and the ambiguity attitude. And the interpretation maps that I discussed now actually generate ambiguity-loving behavior, which at first seems strange to me, but actually I think makes a little bit of sense because things like the winner's curse, we see agents acting overly optimistic rather than pessimistic. Then, I consider dual models which flip things around and create ambiguity aversion. and the relationship between them, and there's the relationship between topology. And the last thing I just want to briefly say is that you could start with a syntactic model and then from that derive a state space rather than starting with an objective one, and understand how the relationship between implication can provide what this state space looks like. And that's actually done in a different paper, but it's worth pointing out that if you're worried about where this objective state space comes from, that can also be dealt with. So I look forward to hearing your questions and comments during the actual conference, and thanks a lot for watching.